Let us now discuss some advanced aspects of cache design. So these will definitely be deeper design choices as compared to some of the design choices that we have seen, particularly in the first section, where we discussed methods to improve the performance and efficiency of a cache, such as critical word fetch, early restart, and others like a victim cache. But these ideas are slightly more advanced. So let's start with asking a question. Let us say that a cache access takes 5 cycles, which can be the case, particularly if we have a large L1 cache and we have a reasonably aggressive clock cycle time. So in that case, it is very much possible that we can have a cache that takes 3, 4, 5 cycles to access, and definitely a larger cache such as the L2 cache can take even more time. So the critical question over here is that do we wait for 5 cycles for the next access? So the answer is no. So we have already answered this question when we discussed in-order pipelines, and clearly the answer here is no, it is not going to be the case. What we will instead do is we will pipeline the cache, which means that at least we can accept a new request, if not every cycle, then once every 1 or 2 cycles. The latency can be high, as we have seen, but what pipelining gives us is that it gives us high throughput. All right. So this is an important point to bear in mind, that even if the latency is high, that's not desirable. But nevertheless, if we pipeline the cache, at least we can ensure that our throughput is high. And so many applications that are throughput dependent will at least be benefited from this design. So let us look at a simple idea of how to pipeline. Look at the tasks that are involved in a read operation. So in a read operation, right, one second. So in a read operation, what happens? That we have a parallel tag and data array access. So we have already discussed this, and this was a very beneficial design choice. The reason being that, of course, we do waste a little bit of power, but at least we get the k data blocks in a k-way set associative cache in the same cycle. And once we know which tag matches, we can then choose the appropriate data block. So this is, of course, the first part. Let us call it stage 1. Then stage 2 is when we compare the tags. So the comparison is also a slow process, because in comparing, what do? We basically take two tags and we subtract one from the other. So that is one way of comparing. The other is that we just compare the bits, and then we compute an XOR. And if, let's say, any bit pair differs, then the values are not the same. So regardless of how we do it, this will take one full substage. And finally, once, if there is a match, if we find a match, then we select the data block. So what we can do is we can take this simple design and we can pipeline it. So pipelining does not require any additional circuitry. All that we need to do is we need to insert a pipeline latch between adjacent stages, right? A tag array, data array access, tag comparison, and data block. All right. So something similar can be done for a write operation. So what we would do is that for a write operation, we will access the tag array. Then we compare the tags and we effect the write in the data array. So of course, if we have a read and write to the same address, some forwarding will be required. So that forwarding logic needs to be added. So let us now see what else I have on this slide. So what we can do is that we can further add more pipeline stages. So one worthy idea in this space is to pipeline the SRAM access, right? So if you would recall, in the SRAM access, we have this huge row decoder. The input is the address. And then of course this sets the appropriate word line. Then we go to the SRAM array. We read whatever that needs to be read. And by that time we are expected to have configured the column mux tmux. Finally, the sense amplifiers read the data and the data comes out. So we can, in principle, pipeline the decode process in the sense that we can add a huge pipeline latch over here where the decoded address, so the decode lines, would be sort of temporarily stored in that latch for one cycle. So of course here the latch has to be very large, right, roughly the size of the decoder, because storing one bit is not easy if let's say we want fast access. So it'll have to be one D flip flop per bit, and this does cause issues in terms of a high area footprint, and also it adds to the capacitive delays of the word lines and so on. So because of that, pipelining the SRAM access any further is not advisable. So what do we do then? What we do then is that we look at other kinds of optimizations, which brings us to our second optimization. This is another idea which is called a non-blocking cache. So let's say that we have a cache miss for a certain block B. So if there are later cache accesses, what happens? So if they are to different blocks, well, they can go through. But let's say if they are to different memory words within this block. So what do we do? Do they actually stall? So what we do is that accesses to other addresses need not be blocked. That is the key idea. That accesses to other blocks need not be blocked. But let's say that for the miss block, what we need is we need to simply store or record all the accesses that are being made to different words of the miss block, such that when the miss arrives from the lower level, all of them can be serviced in one go. So to do that, what we do is we add a new data structure. So this is not a data structure in a data structure sense, it's a hardware structure. So let's call it a hardware data structure, okay? So let me define something, but this is of course pure hardware, it's no software, okay? So, but I love the word data structure because it uses similar concepts, but I do agree that this is kind of an abuse of the term. So let's call it a hardware structure, okay? So even though I would have been internally motivated to say hardware data structure, but in the interest of keeping things consistent and simple, let's call it a hardware structure. This is an MSHR, a miss status holding register, which has a rather intricate structure which we will see next. So the MSHR is associated with a cache. So it keeps track of the misses of the cache. Each entry of the MSHR has two fields. If we look at it from the top level, the first field is the address. So this is the block address, that is the first field. And the second field is a miscue. So whenever we have a miss, or let's say whenever we have a read or write access, the MSHR is always checked. So the block address is looked up very quickly, and the MSHRs are typically very small structures. So they have maybe 4, 8 or 16 entries. So this structure can be very well fully associative as well, right? It can be. There is no harm in that. And furthermore, each entry has a miscue. So the miscue, each entry of the miscue is called a miscue entry. Its fields are as follows. The first field is read or write. So this field refers to whether the particular access is a read or write. So this will be a 1-bit field. Next we have the word address. This is the address of the specific word within the block which led to a miss. So this is the word address. The next is the tag. So the tag is mostly useful for a load instruction. So in a load instruction, this tag, and also this is useful for the L1 cache. So this is basically the tag of the instruction, the tag of the register, right? The physical register ID of the register that caused a miss. Why is this needed? Well, this is needed because when the value of the load comes back from the lower level, we can immediately send the address to the processor, send the load value to the processor, and along with this the tag will go because the tag will indicate which load it is. And the final field is a store value, which is the value that needs to be stored. So this again is useful for stores. So for every address, what we do, so for every address meaning a block address, we have an associated miscue where all the miscue entries are stored in first in first out order, in FIFO order, right? And so there is applied one after the other in FIFO order after the block comes from the lower level. So a little bit of detail about the operation of an MSHR. So when there is a miss in a cache, an entry is created in its corresponding MSHR. So if there are no free entries, right? So assume that the MSHR is full and we can't create a new entry. Then of course the request blocks. And so then from a non-blocking cache, the cache becomes a blocking cache. But of course the MSHR should be large enough such that this particular scenario does not happen. Or let's say it does not happen frequently. So what we also do is we also create an entry in the miscue, which will be the first entry. This is known as a primary miss. So once a primary miss is there in the miscue, what we need to do is that we need to add additional entries if there are subsequent misses before the data actually arrives. So these misses will be known as secondary misses. So if a secondary miss is a write, what we do is we just append it to the tail of the miscue, right? So basically what we do is that if we assume it's a queue, so then we just add a new entry to the tail of the miscue and the write just remains there. If it is a read, similar to a load store queue, we search for all earlier writes in the miscue to the same set of bytes. If we find an entry, then there is no reason for us to queue the read. What we can do is we can just forward the value exactly the same way we would do it in a load store queue, and the processor can resume. So in this case, the operation of the LSQ and the MSHR is the same. Else, otherwise, we enqueue the entry. So we add the entry to a queue, and again it remains in the queue until the entire block comes from the lower level. So what was new in this slide? The forwarding aspect was new in the sense that the MSHR has a forwarding capability similar to an LSQ. So this aspect was new. Now let's come to the third idea. So the third idea is a new kind of a cache design, which again, if you can see, it again comes from a simple data structure concept. So after all, a cache, what is a cache? So a cache, a direct mapped cache is like an array, right? So its data structure analog will be an array. So consider a direct mapped cache. The analog for a direct mapped cache will be an array where we know the exact index, we go there, we see the value is there or not. If it is there, we access it, else we declare a miss. Even a set associative cache is somewhat like an array, but a fully associative cache is like a hash table. So in this case, what we do is that, well, a given entry can be present anywhere. So we use a CAM array, a content addressable memory array, where we can search which entry has the particular address, and if we find it, then at least from the top, it does appear to work as a hash table, in the sense that we use a baseline CAM array, which again addresses it by its content. All right. So here again, the big broad idea is rather different in skewed associative caches. So the direct competitor for a skewed associative cache is a regular set associative cache, which is a combination of an array and a hash table, or a hash table implemented on top of an array, where essentially we are pointed towards a set of locations, and let's say it's a k-way set associative cache, then we are pointed to k locations. We go there and we then see if the address is there or not. And of course, conflict misses cause a problem, in the sense that, let's say if it's a four-way set associative cache, but there are 5 blocks that map to those 4 ways, then continuously one of them will get evicted, and there will be a timing penalty. So what we do is, instead of a regular hashing scheme, where a regular hashing scheme is that we take an address, we extract some bits out of it, we might further mangle the bits, and then we use it to access an array, some location, and then we do a local search, as we do in the as we do in the set associative case. So this is kind of an extension of the basic hash table idea, even though some of you may not entirely agree with me, in the sense that you might say that, look, in the hash table we only search for a few locations, search in a few locations, but in a fully associative cache we actually search all the locations. I agree with you, the comparison is not 100% accurate, but still a hash table searches on the basis of content. This is something that a CAM array does, and that's why I have created this comparison, even though there can be arguments against this comparison. But broadly speaking, a set associative cache does embody the spirit of an hash table implemented on an array. There is another way of hashing, which is known as cuckoo hashing. So in cuckoo hashing, what we do is that, instead of using one hash function, we actually use multiple hash functions. So what we can do is, we can divide a cache into 4 subcaches. Given an address, we can compute 4 different functions on it, f1, f2, f3 and f4. So they would essentially produce different locations within the cache, right? So if you can see, all of these locations are all different. So there is a beautiful property which I will come to next. The beautiful property is, consider 2 addresses. Again, they are block addresses in the context of this discussion. So let us say that they are colliding in subcache 1, in the sense f1a1 is equal to f1a2. So this indicates a conflict miss, with most likely, or with a high probability, in the second subcache they will not collide, in the sense they will map to different locations. f2a1 will not be equal to f2 of a2. So they'll map to different locations. So the key important insight over here is that, if they conflict in one subcache, most likely they will not conflict over there. So what we do is that, if already, let's say, block with address a1 is there in one subcache, then what we do is, we go to the other one, and there we'll not have so there we'll have another location and we put our block over there. So this really reduces the chances of conflict misses, and this is an extension of the basic cuckoo hashing idea, because as I said, what is architecture? It is essentially a hardware wrapper over what is fundamentally a data structure concept. So the key important question over here is that we need to compute these functions f1, f2, f3 and f4, right? Such that, of course, this property holds that if there is collision in one subcache, we can go somewhere else. All right. Replacements are tricky. We will see in a second why. So we need to do something called a cuckoo search. So assume we want to add the block B at address A. So we will first check the four locations F1A, F2A, F3A and F4A to check if they are free. If one of them is free, well fine, we put the block over there. And in this case, accessing the skewed associative cache does require more power, in the sense the four functions need to be computed, and then we need to access the different subcaches to see where exactly is the block, right? Because it could be there in any subcache, right? So in this case, while inserting an entry, if any of these entries is free, then we insert the block over there. But let's assume the worst case, that none of these entries are free. So what we do is we evict the block B dash with address A dash, that is, let's say, stored at F1A. All right. So then we insert the block B in the first subcache at F1A. So now the idea is that since B and B dash had a conflict miss in subcache 1, they will not have conflict misses, right, in other subcaches, which means that even the likelihood of had we not used this, what would have happened is that pretty much all four of them would have been like the same set. So there would have been conflict misses for B dash in the other subcaches as well. But because we use different mapping functions, what we can do is we can try to accommodate B dash at these locations, right? Recall that block B dash, the address of block B dash is address A dash. So we can try to accommodate it at these locations, F2A dash, F3A dash or F4A dash, right? So what did we do? Well, since we didn't find a free location, we essentially tossed block B dash out from subcache 1 and we put in block B. Now the question is, what do we do with B dash? So B dash again will map to three other locations in the three subcaches, which are F2A dash, right? I mean, it might be better to F2A dash, F3A dash and F4A dash. These locations are most likely not same as F2A, which we know to be full. F3A dash is most likely not the same as F3A, which we again know to be full, which is, and F4A dash is again not the same as F4A, again with high likelihood, and F4A is something we know to be full. So these locations are other locations, and it is very much possible that one of these locations may be free. Or we can randomly choose one. If that is not free, we can look at the other two. But it's very much possible that one of these locations may be free and block B dash can be put there. So let's assume again the worst case, that these locations are not free. Well, we can do the same. We can put in B dash in one of these locations, toss out the block B double dash, which was over there, and try repeating the process, because B double dash will again with high likelihood map to another set of different locations, right? And once it maps to another set of different locations, ultimately after maybe a few rounds, we will find some free locations. So this method is called cuckoo search. So what I would advise all of you is that you read up regular hashing. So regular hashing again has two variants. One is called chaining and the other is called linear probing. So we are not really doing chaining over here. Uh, what we are doing is more like linear probing, which is similar to a set associative kind of access scheme. But the other access scheme, which is a slightly different paradigm in the world of algorithms and data structures, is cuckoo search, which is exactly something that I described. If you are not able to understand what I described, what I would like to advise you is kindly take a look at the cuckoo hashing and cuckoo search algorithms, and then you come back. All right. So it's an interesting thing of why do we say what is the, why do we say it's a cuckoo search and why not some other bird? So the interesting story is that the cuckoo is actually a very clever bird. So what the cuckoo does is that it lays its eggs in a crow's nest, and a crow's eggs and a cuckoo's eggs look more or less the same. So unbeknownst to the crow actually helps incubate and hatch the eggs of the cuckoo. And once baby cuckoos are born, then their mother comes and they are collected and they fly away. So we are in a sense playing a similar trick over here where we are having different hashing functions and we toss around blocks and so on. So this is pretty much the history of this algorithm, which of course has found an implementation in the skewed associative cache scheme. So as I said, we can do this tossing around several times, but of course, if the entire cache is full, we'll never find space, but we can do it a few times, and if we don't find free space, then we can evict the block to the lower level. So that option always exists. Now we come to our fourth mechanism called wave prediction. So wave prediction is rather interesting in the sense it takes us very close to the actual implementation, right? Very close to a designer's point of view. So what is the default mechanism in, let's say, set associative caches? We read all the tags and blocks in a set simultaneously. Again, why do we do that? We do it for performance reasons. We compare the tag part of the address, right, with each of the tags. So you pretty much do more work than what is required. Whenever that is the case, we end up burning more power than what is required. So let us propose a brilliant idea over here. The idea is that we predict the way in which the tag will be found. So if there are k ways in a set, we try to predict. We say that look, maybe in a second way the tag will be found. We access that way first. So bear in mind that we do not read all the tags at the same time. We don't do that. We predict in which way we will find, we access that way first. If the tags don't match, we access the rest of the ways, and then we declare a regular hit or miss. So the advantage over here is that the additional energy that is spent in reading all the tags and blocks in a set, and that too simultaneously, that energy is not spent, right? So we can save on energy subject to the fact that our predictor is accurate enough. So that is an important insight over here, that if our predictor is accurate, then what we can do is that we can have a more power efficient version of a set associative cache, right? So the key important point here is to design an accurate predictor to tell us in which way we will have a hit. Let us now discuss the methods of wave prediction. So the basic idea is that if the memory address is available, then we use it, because after all the memory address will be the best predictor in almost all cases for the way that you would expect to find it in. However, there are pipelines where the memory address may not be available when we initiate wave prediction. At that point, we need to proceed on the basis of some other information, right? Some other piece of information. We need to proceed on the basis of that. So I outlined two approaches. So in one approach, we predict based on the program counter. So we use a mechanism that is very similar to branch predictors that uses the PC address to make a prediction. So in this case, we have a predictor which is extremely similar, and we provided the PC. It predicts, and what we get out is the way. A major shortcoming of this approach is that for the same program counter, the addresses keep on changing. So if the addresses, if the memory addresses keep on changing, the ways will also keep on changing, and the predictability of this source is kind of low. So what we do is when we do not have the address, we use an estimate of the memory address, right? The estimate is computed using a different mechanism. The mechanism is as follows. Let me explain with an example. So let us assume the load instruction is of this type: load into register R2, 12 R1. So then what we do is that we can divide this into 4 stages. So let me first look at the stages of the regular pipeline, and then I will talk about the additional stages. So one stage is where we read the registers. So in this case, we read the registers R1 and R2. So these are the source registers, we read them. Then the next stage, we compute the address. So in this case, we add 12 to the contents of R1. Now we have the memory address with us. So in this case, we check for load store queue forwarding. We can additionally have another stage to convert it from convert the virtual address to the physical address. So this depends upon what we store in the load store queue. So if within the same thread, different virtual addresses can map to the same physical address, then we need to store physical addresses in the load store queue. But otherwise, if we are guaranteed that different virtual addresses will point to different physical addresses, we can use the virtual address to address the load store queue, and in parallel we can do the translation, right? So I'm not showing that because I will show an optimization to this process a few slides later. But in any case, one cycle is definitely needed for load store queue forwarding, and then we access the D cache. And this accessing the D cache itself can take multiple cycles. So let us now look at an alternative timing where our wave prediction, the time it takes to do wave prediction, is actually closer to 2 cycles than to 1 cycle. So there what we will see is that if we have the address at this point of time, we cannot afford 2 cycles to do the wave prediction and then access the D cache, so that will not be possible. So what we should instead do is that we should compute an approximation of the memory address. So the approximation can be computed like this, that we take the contents of the base register, which in this case is R1, this is the base address, and we compute an exclusive OR with the offset, which is 12. So this can be done quickly. I mean, this is much faster than addition, and so this can be done independently bitwise. So after that, the rest of the time can be spent on doing wave prediction. And the wave prediction will use similar tables as we use branch predictors. So the rest of the time, which will be roughly 2 cycles, right? So we are treating this as a composite 2 cycle stage. So this can be used to come up with the way when we access the D cache. Of course, alternative organizations are also possible. So there will be some questions at the back of the chapter which also looks at different ways of organizing the timing. But if we take a look at this particular example, what we can immediately conclude is that we do not have enough time after the address to do the wave prediction, so it needs to happen in parallel. That is why we need an estimate where we use a XOR function like the G-share predictor to provide us an estimate of the address. So let's say if, from the LSQ forwarding stage we decide that we need to access the D cache, then the way can come from here. We first access the predicted way, which is fast. If let's say we do not find the data there, then we access the rest of the ways. Alright, now let's come to our next optimization after way prediction, which is loop tiling. So loops are very important in code, primarily because a program spends most of its time executing loops. Alright, so most of the time of a program is spent in loops, and particularly if we have large loops that access large arrays that are stored in memory, on a system with caches, running such large loops becomes a problem. So we need to first answer a question: how is a 2D array stored? So there are two ways of storing a 2D array. One is the row major order and the other is the column major order. Because after all, an array can be 2D, but the memory, the way that we see it, is basically a 1D array of bytes, right, with increasing addresses. So for a 2D array, what we can do is we can store the first row, then the second row, third row, and so on. So many programming languages use the row major order, but what is kind of more common, I would say slightly more common, is the column major order. In this case, we store the first column, second column, third column, and so on, right? So that is primarily the way that data is stored. And so what happens is that if let's say an array is stored in row major order and then we read it column wise, it will cause a lot of cache misses because essentially there is no locality, right? So spatial locality is not there. But if an array is stored in column major order and we access it in column major order, then of course we'll have good performance because we can leverage the effects of spatial locality. So let us consider matrix multiplication, for example. So this is a standard code for matrix multiplication, where we are multiplying two n cross n matrices. The final matrix is also n cross n, so A multiplied with B is producing matrix C. So the final, as you can see, the final result is being written here, and this loop over here basically computes, does the multiply step. So what we do in a matrix multiply step is we take a row, multiply it with the corresponding column. So we take the ith row here, multiply it with the jth column. It's a pairwise multiplication and addition. That's the reason we have the plus equal to over here. And finally, after the pairwise multiplications and additions, the final sum is stored over here. So when arrays are large, let's say they are very large, they are much larger than the size of the cache. So this will actually lead to a very inefficient traversal, so to speak, because just take a look at this array. So in this array, we are essentially traversing the array in row major order, array A in row major order. But here, what we are doing is we are choosing a column and we are traversing that array in column major order. So we are clearly not taking advantage of spatial locality. Of course, some programming languages can be smart and some compilers can be smart in the sense that they will store this array in row major and this array in column major. But typically that's not the case. And the second is that even if they were, it is possible that a single row is much larger than the size of the cache, which can be the case with large data sets. So there is a need to convert this code into a more cache friendly version. So the method to do that is called loop tiling, which we will discuss. So this is also called blocking. So we will see why it is called blocks, but let's look at the idea. So what is the idea? Well, the idea here is that let's first look at the default scheme. In the default scheme, we take the ith row and the jth column, we multiply the elements pairwise and then we add them, and the final result is stored over here. So then the other thing is that instead of the other idea, which is in our sense a novel idea, which is loop tiling, is that we don't consider an entire row or an entire column. Instead, what we do is we consider a small block of data. All right. So the small block of data can start at the coordinate IIKK, and then basically the size of the block might be B rows on this side and B columns on this side. And we consider a similar block which again starts from here. So what we do is that we take one small row over here, we take one small column over here, we multiply them. So we'll produce a set of partial sums, and those set of partial sums can then be used to basically, so those are anyway part of the matrix multiplication, right? So those partial sums will be used to update the final sums, which is the final sum is being referred to as Cij. So they will be used to update the values of Cij in the final matrix, right? So we'll have to consider many such small blocks. In each block, we perform a regular matrix multiplication, which means we take a row, take a column, multiply them. But unlike the previous default approach, where after one iteration we finally have the value of Cij, in this case we will not have. Rather, we'll have partial values for all the cells within a block, but they are stored, and this process is repeated until all the pairs that need to be multiplied are done. One small advantage of doing this is that if, let's say, the size of this block is small, the entire block can fit in the cache. Similarly, this entire block can fit in the cache. So all of these traversals, even if because of the block effect, even if, let's say, spatial locality is lower, but at least it is guaranteed that all of the accesses will hit in the cache, and so basically this will be a very fast access. Now let me show the code for tiling. So the key idea is that we have 6 loops instead of 3 loops. The 3 loops at the top, which is the iterators II, JJ and KK, they traverse the arrays at units of the tile size. So we are of course making an assumption over here that n is divisible by b. Otherwise, of course, we can add some dummy elements, or we can do a little bit of algebra to take care of it. But let's assume for the sake of simplicity that n is divisible by b. So we divide the matrices basically into small tiles, as you have seen over here, that they are being divided into small tiles. And each tile, each p cross p tile is assumed to be small enough such that it fits within the cache. So what we do is that we are multiplying two matrices over here, right? And whenever we multiply, we consider the ith row over here and the jth column over here, where k is the iterator. So in this case, instead of the ith row, we consider a set of rows, which is basically the tile size over here. So we consider b rows. And similarly, for the other matrix, what we do is we consider a set of columns. Within the right, so basically within each row, we don't consider the entire row, but we consider a part of it. And similarly, within the set of columns, we don't consider the entire column, but we consider a part of it. All right, so that is given by this third parameter, which is kk. So this for us is the tile that we considered, and we perform all the multiplications within the tile. So to perform all the multiplications within the tile, what we do is that we iterate within the tile. So we have 3 loops over here where we perform an iteration within the tile. So we iterate from the locations II to II plus B, right? So II is considered the starting location of the tile. So this is also shown over here, where the starting location of the first tile is IIKK and other one is KKJJ. So all that we need to do is we need to iterate within this tile and we need to perform the multiplication. So just look at the three iterators. We are iterating from II to II plus B, JJ to JJ plus B, and KK to KK plus B. So once that is done, what do we do? Well, once that is done, we have the exact indices I, J, and K. We perform the multiplication. So of course, note the plus equal to sign. So the multiplication over here is just adding to the partial sum, which is Cij. So once all the additions are done, you can say Cij is complete, and that would happen once we consider all the relevant tiles. So it is in fact quite easy to prove that this multiplication is doing exactly the same thing as matrix multiplication. And so this is something that can be proven. And it's, so if you think about it, let's say that n is divisible by b. So the number of iterations of the top three loops are essentially n cubed by b cubed. And the number of iterations of the bottom three for one given combination of this is essentially b cubed. All right, b times b times b. So if I multiply both, we still have the n cube multiplications and no multiplication happens twice, right? So, and then you can also verify what exactly we are adding and how we are computing Cij. So using this, it is possible to prove that both the algorithms are identical. And of course, proving it more formally is left as an exercise for the viewer. Well, a burger question over here is that prove that the algorithm is correct. So this can be done. We need to just prove that the same set of multiplications are done, no extra multiplication is done, and the results are computed correctly. All right, now let's come to the question that we had kind of left unanswered when we discussed wave prediction. So what we had discussed then is that any internal address is a virtual address which needs to be converted to a physical address. So we need to compute the address, it needs to be translated, and the translated address needs to be used to access the Dcache, right? So the key insight is that we need to spend an additional cycle translating the address after it has been computed, which is this cycle. So this cycle is essentially at least one cycle of delay, because here we access the TLB between the address compute phase and the Dcache accessing. But of course, to improve performance, after computing the address, we also access the load store queue, so that can be that phase can be overlapped with this phase, subject to the fact that we store virtual addresses in the load store queue. But storing virtual addresses in a load store queue is tricky. It does have correctness issues, which were discussed in a previous slide. So now the question that we ask is, what if we don't need any translation to access the correct set in the L1 cache, right? So what if in the L1 cache we actually don't need any translation? Well, does it mean that we send the virtual address to the L1 cache? That will cause a problem. The reason it will cause a problem is that the next time that another thread runs on the same core, another process runs on the same core, right, thread or process actually, if they are using the same virtual address, there will be a problem, right? So there will be a problem. So let's discuss this in some detail, but we are seeing that it is possible. But well, the idea is that if there is a different thread or process that uses a different virtual address space, right? If it's using the same virtual address space, there is no problem. But we can always have a thread from a different process that is that has a different virtual address space. So unnecessarily, if we use a virtual address to access the cache, we'll get a wrong answer. So the overlap problem will come up. So now we see that there is a fundamental trade-off here between performance and correctness. We would, of course, not want to compromise on correctness, but we would also like to use the virtual address in accessing the Dcache. So let us see how to do it. In some cases, we can get away with it. So where can we get away? Let's understand this process in some detail. See, if I have a 32-bit or 64-bit memory address, I would typically break it into a page ID and an offset, where the offset is typically 12 bits because the size of a page is normally 4 kilobytes. If I were to consider a 32-bit address space, the page ID would be 20 bits, and then the frame ID will also be 20 bits, but of course it can be different depending upon the size of the physical memory. But let's say that the maximum size is limited to 20 bits. So if I were to look at the offset in some detail, I will see that there is a little bit of hidden magic in here. So what I can do is that if I take my cache address, if let's say these 20 bits of the frame ID correspond to the tag, and the offset corresponds to the byte offset within the block and the set index, then the offset which will actually not change, right? So basically the offset is not dependent upon the virtual to physical mapping. So essentially this part is something that does not change, whereas this part is the one that is actually mapped. We can use the offset to find the set, right? So basically so the tag of course will come from the mapping process. But what we can do is we can use the offset to at least access the correct set within the cache and read out all the data blocks and tags within the set. Simultaneously, we can do the mapping. So let me explain this in some more detail, because this is a very, very important mechanism. So what am I trying to say? Well, what I'm trying to say is that in any virtual to physical translation process, there is a part of the address known as the page offset. So I should call this the page offset, and I should call this the block offset. So, sorry, the byte offset over here. So the page offset remains constant if my addressing scheme of the cache is such that the tag comes from the mapping phase and the rest is a part of the offset, then the set index is not dependent on the mapping, right? So the key important point is that the index, which is the set index, is not a function of the mapping. And then the brilliant idea is that I can use this index to access all the ways in the set, read my tag and data blocks, and at the same time also do the mapping. So what is it that I'm doing? Well, what I'm doing is that my tag will go to the address translation module, but my index can come directly from the page offset. This can be used to read all the tags of the tag array as well as read all the blocks from the data array. In parallel, so essentially what am I doing? I'm accessing the tag array, I'm reading the data array. In parallel, I'm doing the address translation. So I'm overlapping all of these within the same time window. After that, I can perform the tag comparison because I'll already have the tag. So I'm essentially saving a cycle over here, that instead of this process being sequential where I translate the address first and then access the cache, I'm deliberately introducing an overlap over here to give me that extra, to reduce that extra one cycle. Then I do the tag comparison and I select the appropriate data block. So this part is the same. What is actually different is the earlier part where I was able to save one cycle by creating an overlap over here. And the reason that I could create this beautiful overlap is basically because the tag part of the access actually came from the mapping phase. So this is not a generic mechanism because this depends on the size of the cache, the size of the set index, and so on. So that's the reason for an L2 cache, this is not a very reasonable idea. But if you read the book and you will see a working example given, you will find that for most typical L1 cache sizes, This is a very reasonable idea. That is why many commercial processors actually use this mechanism. All right. So next we will discuss a novel idea called trace caches. So in trace caches, the idea is that can we totally sideline the branch predictor and the decode unit and just store an unrolled trace of instructions that can be directly fed to the renaming stage, right? So can this be directly done? So we will look at that next.